Good day everyone. I'm going to present my work about using bomb-calorimetry to inspect the water content of an emulsion fuel. The keywords of this research are bomb-calorimetry, emulsion fuel, and water content. This work was performed in November 2018 during my PhD study at the University Technology Malaysia in Kuala Lumpur. I am the main contributor of this work, Dani Afianto Sugeng, and I am currently a researcher in the field of fuel and energy in BPPT, an Indonesian government research agency. So let's start with the overview to build my case for this work. Emulsifier is defined as a naturally immiscible mixture of water in fuel with the presence of surfactant or emulsifier like twin or span 80. Use of this kind of emulsion fuel requires no modification of the engine. A variant of emulsion fuel is called non-surfactant emulsion fuel. This term implies that the produced emulsion requires no surfactant. Therefore, it immediately separates into its water and fuel phases. To apply this kind of fuel, we need an inline mixing system which will prepare the water and fuel as per the requirements of the engine. In this work, we will focus in the so-called non-surfactant Water-in-Diesel emulsion fuel, in which we are using diesel engine to test the fuels. The main feature of an emulsion fuel is the so-called micro-explosion. We can picture this phenomena as the explosion during food frying. When we fry food, strong explosion will occur when you put moist cold food into a pan filled with hot frying oil. Similarly, in a combustion chamber of an engine, the emulsion enters the combustion chamber in an atomized form, like this. The water droplets enveloped in the atomized fuel will be the first to reach the boiling point, and due to the sudden temperature change, they instantly vaporize, which resembles an explosion. The explosion causes the atomized fuel droplets to undergo a secondary atomization, which in turn causes the fuel to be more dispersed in smaller sizes, and this potentially enhances the distribution of the fuel in the combustion chamber and also the combustion. The benefits of an emulsion fuel in general include the lower gaseous emission of NOx and particulate matter. It also potentially lowers the brake-specific fuel consumption, which translates in the increase of the brake thermal efficiency. For the non-surfactant emulsion fuel, all the benefits are there, and it has an additional benefit of no surfactant added costs like material costs and processing costs. However, to produce the emulsion, we need an inline supply system. Various systems have been developed to create the inline supply system. In 1949, Mixer employs the high shear mixer to create the emulsion. The system has three injectors. The first is the diesel, and second is the surfactant nozzle, and the third is the water. In 2011, Kadir devised another system which employs the ultrasonic transducer. Water and diesel will enter through this nozzle and then homogenize in this ultrasonic transducer and exit the system to the engine through this nozzle. 2014, musim ini device, the so-called RTES, or real-time emulsion fuel supply system, which employs both high shear mixer and ultrasonic transducer. This is the device, the RTES, and it will supply the emulsion to the electric generator. Water comes from this tank and diesel comes from the other tank. This system has been proven to operate in a small generator engine, small electric diesel engine, and a light-duty lorry. The system has a system of reflux or recirculation of the emulsion. So from the yellow one is the internal recirculation, while the green one is the return line from the diesel engine. This internal and external recirculation causes the water content of the emulsion to constantly change during the operation. So how does the water content of the emulsion of non-surfactant emulsion fuel is calculated? For the normal emulsion fuel with surfactant, it is refilled because the emulsion fuel is prepared somewhere else and then put to the fuel tank. Whereas for the non-surfactant emulsion fuel, the water content is averaged from the fuel consumed divided by water consumed. Or if sample is provided, we can distill with an ASTM D95 distillation method with this device. Next, we define the problem statement. Because of the return line and internal recirculation in inline emulsification system, the ad hoc water content is unknown. So the water content at a given time is not known because it changes all the time. Therefore, the relationship of water content and emission is difficult to quantify. It is the objective of this study to investigate whether the bomb-calorimetry and weighted average method can be applied to predict the water content. And also, bomb-calorimetry can be completed within 15 minutes. So it will deliver speedier results in contrast to 2.5 hours for ASTM D95. And now I will discuss the methodology for this work. For the purpose of the study, we prepare 9 samples, which are, the first is D2M. This is the Euro 2 diesel standard of Malaysia. And then water. The third is SPAN 80. Fourth is diesel mixed with SPAN 80 only. And then 5 is called E5, that is the emulsion of diesel and SPAN 80 and water. And then the non-surfactant emulsion fuel with 3%, 5%, 8%, and 10% water. The sample look like this. Sometimes it's less or more milky than this. All the samples are homogenized in so-called ultrasonification using a generic ultrasonic bath. The homogenization is done in 5 minutes, and 2-gram samples are taken from the middle of the vial using a pipette. After the homogenization, The samples are sent to the Cal2Eco bomb-calorimeter, 2-gram sample, and quadruplicate for reproducibility. Each sample is done in 4 replication. The weighted average method is performed to estimate the water fraction in an emulsion, which is derived from this formula. The total higher heating value of the emulsion is the sum of the product of higher heating value of sample A and higher heating value of sample B divided by the total mass of the emulsion. And it is derived to be this formula. The higher heating value of sample A subtracted by the higher heating value of the total emulsion divided by the higher heating value of the emulsion. Next, we will discuss the results. The result of base ingredients are, for the diesel, it is 46.48 megajoule per kilogram, while water, while we tested, it did not fire, so we assume that the higher heating value is 0 megajoule per kilogram. Whereas span 80 also did not fire, and we use the value of 0 for the calorific value of the span 80. The calorific value of each sample is shown here. The blue one represents the non-surfactant emulsion fuel with 10, 8, 5, and 3% of water. The lowest is 41.91 for the 10% emulsion fuel and 45.06 for the 3% non-surfactant emulsion fuel. E5 show the value of 44.57, while diesel and span 80 45.31. Neat diesel accounts for 46.48 megajoule per kilogram. The drop in higher heating value for each sample was obtained from the experimental values. For the non-surfactant emulsion fuel, 10, 8, 5, and 3, we get for 10, we get 9.82 water. For 8, we get 8.23%. And for 5, we get 5.15%. For the 3, we get 3.05%. So we can see that all the values for non-surfactant emulsion fuel is close to the actual water content. While for E5, the water content is lower than the calculated water content is lower than the actual. While for diesel and span 80, we get higher water content, 2.52. So the deviation in the non-surfactant emulsion fuel is maximum 3%, while for E5 the deviation is minus 17.8%, and for the diesel plus span 80 we get an error of a deviation of 26%. So we can conclude that when surfactant is involved, the values is not predictable. So the conclusion are that bomb-calorimetry delivers good estimates within plus minus 3% of the water content in a non-surfactant emulsion fuel. While for emulsion fuel with surfactant, the bomb-calorimetry method is less predictable. Sometimes it is lower and sometimes it is higher. And last, the results were yielded in maximum 15 minutes. So this will be suitable for engine tests where we get a lot of samples. Thank you for watching my presentation.